So, some of you got an introduction to this at the tutorial on Friday. Some of you didn't, you weren't there. But what we were looking at was Dirichlet's theorem. Okay, which is this question 3 on page 69 of the notes. So, just to give a quick review, early on at the start of chapter 3, we proved what's the most kind of famous result in introductory number theory. We proved that there's an infinite number of primes. Okay, so extremely quickly, Euclid's proof for infinite number of primes how did that go? Well, it was proved by contradiction. Okay, it's proof by contradiction. The main idea, or the quick sketch of the proof, was assume there only exists a finite number of primes, P1 up to Pn. Then when you're doing proof by contradiction, you begin by assuming what you're trying to prove is wrong, and then you attempt to squeeze out of that, get a contradiction out of that. Clear contradiction does not work. So we assumed there was only a finite number of primes. We then considered this number n, which was the product of all the primes, then add 1. Of course, the product of all the primes is definitely a composite number. But when you add 1 to it, well, maybe it could by fluke be a prime number, but what we can say is it certainly has, n has at least one prime factor. Now, it must be one of the PIs because we've assumed there's only a finite number of primes. Okay. So let's say it's called PI for some I between 1 and n. It must be one of those P's because we've assumed there's only a finite number of primes. But then we know that PI divides n, but we also know that PI divides the product, P1 up to Pn. And therefore PI has to divide 1. Because 1 can be written as a linear combination of those two. 1 is equal to capital N minus that product. One is capital N minus the product. So then you get that PI divides 1. Well, that implies that PI is equal to 1 because 1 is the only positive divisor of 1. But by now we've argued ourselves into a corner. This looks wrong. You can't have a prime number equal to 1 because the primes are by definition numbers strictly written. 2, 3, 5, 7, so on. Okay. So this is a clear contradiction. Now the steps that argue towards that were fine, except for the very first one. Okay. So star cannot be made. Not a tenable assumption. Okay, so if you can't assume that there's a finite number of primes, that means there must be an infinite number. So there exists an infinite number. Okay. So that's, as I say, that's probably the most, the first famous result in number theory. There's an infinite number of prime numbers. Now, Dirichlet's theorem was introduced, and I introduced it in a lecture last week. Dirichlet's theorem deals with, I'll use the notation there, an plus b. So that's an arithmetic progression. It's got some initial term, which is represented here as a plus b. Or you could begin the counting at 0 if you wanted to begin at B. But maybe more natural to begin it there. So it's got some initial term B, and you add A on each time to generate the next elements in the sequence. So you start at some point, and then you just go by a fixed step size each time, adding on A. Now, there's one case where these are obviously trivially all composite numbers, and that's where there's a common factor between A and B to begin with. So if you know some number, say 5 divides A and 5 divides B, so both of them are multiples of 5, then every single number in this sequence is going to be a multiple of 5. Okay? It's a sum of multiples of 5, so it's going to be a multiple of 5. So in any case where A and B are not co-prime, where they share a common factor, a non-trivial common factor, then all of the elements of the sequence are going to be. All right, we can see then that they're composite. Okay. So if the GCD of A and B is equal to D, which is bigger than 1, then for all n greater than or equal to 1, D is going to divide A times n plus B. So for all n bigger than 1, an plus b is composite. But, okay, that's not Dirichlet's theorem, that's just a simple consequence of the divisibility of linear combinations. Dirichlet's theorem says that if the GCD of A and B is equal to 1, so if they're co-prime, there's no obvious factor we can point to immediately for it that divides all of these elements. Now, even if A and B are co-prime, still, most of these elements will be composite numbers. Most integers are composites. You get a misleading view of that when you just look at the beginning of the integers, because the primes are fairly frequent. But as you go further and further out along a sequence of integers, the primes become thinner and thinner on the ground. Okay, but there is an infinite number. But so if the GCD of A and B is 1, then the sequence an plus b has an infinite number of primes. That's what Dirichlet's theorem says. So that's good. That tells us that the prime numbers, they're ubiquitous in a sense. They're all over the integers. You will find them wherever they may possibly arise. You certainly won't find any in a sequence like that where the A and B have a non-trivial common divisor, because by construction they are all going to be divisible by D. So maybe the first one might be prime, or the first, but after that, none of them are going to be prime. But if you give the sequence a chance, if you arrange a sequence with co-prime parameters, then Dirichlet's theorem says within this sequence you will find an infinite number of primes. So the primes don't avoid any kind of thing. Another way of thinking of this is this thing here is equal to the set of all x, such that x is, say, positive. If you take it that A and B are positive, x is positive, and x is congruent to B mod A. Or maybe it skips out a few x's at the beginning, but it's essentially the congruence class, the positive part of the congruence class of B mod A. So you can also think of it in terms of congruences like that. Dirichlet's theorem says that in any congruence class you find an infinite number of prime numbers unless the congruence class is obviously composite. Okay. I.e., every congruence class has an infinite number of primes. Unless the congruence class is obviously composite. I'll give some examples. What is something obviously composite? Something obviously composite would be, say, x congruent to 16 modulo 20. Okay. You are not going to find an infinite number of primes in that congruence class because everything in that congruence class is divisible by 4. Okay. So x is equal to q times 20 plus 16. So we can definitely say that 4 divides x. Okay? This is a non-trivial greatest common divisor between the representative 16 and the modulus 20. Yeah. So you won't find an infinite number of primes in there. And one that you might, x congruent to, so something coprime to 20, multiple of 9, x congruent to 9 mod 20 will contain an infinite number. Yeah, is that clear? Or at least that's what Dirichlet's theorem says. So any questions just about the statement, just about understanding what the statement is asserting? It's not obvious, but it kind of feels right in a way. I mean, why should the prime numbers avoid the congruence class of 9 modulo 20? We can understand clearly why they avoid the congruence class of 16 mod 20, because everything in it is obviously common by construction, because it's divisible by 4. But there's no apparent reason why you shouldn't find primes in the congruence class of 9 mod 20. In 9 is not a prime, but when you add 20 to it, you find a prime. 9. Okay. 49 isn't a prime, 69 isn't, 79. 79 is a prime. Probably, yep. Okay. So, but proving it in general, meaning for any coprime pair A and B, requires more theory than we have. And if you look at you can see the book by Apostle, which is in the reading list. For a treatment of it. But what we can do, and what is interesting to do, is to pick off certain cases of Dirichlet's theorem. There's certain pairs of parameters A and B for which we might be able to prove it. Okay, prove that there's an infinite number of primes in that sequence or in that congruence class. Okay. For certain pairs AB, we can modify Euclid's argument and also use, okay, so I'm kind of repeating the introduction to question 3 here, and also use quadratic residues. To prove this result. So in the tutorial last Friday, and I won't repeat it here, but we proved that 4n minus 1 contains infinite number of primes. Okay, we worked our way through that proof, stepping through it carefully and looking at all the little arguments we needed to make along the way. But the guidance is given there on page 70. We don't consider multiplying together all the prime numbers and adding 1. Instead, we consider this modified construction of having 2 squared, 3 times 5, product of all the odd numbers up to the biggest prime number of that 4n minus 1, then we subtracted 1. But a similar way of attacking this, we were able to argue that we were able to get a contradiction out of this. So let's have a go at part B. The part B deals with the congruence class of 3 modulo 8, or if you like to think about it, the infinite sequence, the arithmetic sequence 8k plus 3. K gets bigger. So we're considering 8k plus 3. Okay, bigger or equal to 0. Okay. Now this is clearly, it's not obviously composite. It's 3 and 8 are co-prime. Yeah. And we can certainly recognize a few primes in this sequence, because the first one, 3, well, if we say go 0, first one, 3 is certainly prime, 11 is certainly prime, 19 is prime. Ooh, they're all prime. No, they're not. 27 is not prime. Anytime you think you've got a recipe for primes, God, I've got this thing that's giving me loads of prime numbers, it'll fail at some stage. Okay? There's an important example. I must include it and look at it directly, but there's a low degree polynomial you can write down. I think it's only order 4 or 5 or 6 or something. And when you evaluate it at its first 80 values, or first 79 values, it generates a prime every time. And then it fails on the 80th time. So we don't know any way to easily produce prime numbers other than testing each integer for being prime. There's no kind of quick, short formula that we'll get into. What's 27 plus 8? 35, that's not a prime. 43 is? Yeah, 43 is prime. Okay. So there's certainly plenty of primes here. We've got a few. So we're going to imitate Euclid's argument. Okay. So we immediately begin. So we try proof by contradiction. So there's at least four primes here. So we assume that P1 up to PS are all the primes. We know S is at least 4. Observe 4 primes there. But we assume that there's just some finite number of primes in that sequence. Okay. Okay, we hope that's wrong, because we hope to be able to prove that it's got an infinite number. We're assuming for the moment that there is only a finite number of primes. And then we'll consider this number. N is the product of all of them. And multiply these all together. We're going to square the result, and then we're going to add 2. And then we got to argue from here. Something. Well, we're going to discover it. We're going to discover that. So squaring is, well, it's related to bringing in what we know about quadratic residues. Okay. So that will allow us to use, or at least look for results about quadratic residues that we might be able to use here. So certainly, so we think of, or we consider the prime factors K, the prime factors Q of N. Now we can't immediately say, oh, Q is one of the PIs, therefore this PI divides 2. Right, because these P1s up to PS are only some of the primes. They're just all the ones that are congruent to 3 mod 8. We don't know anything yet about the prime factors Q of N necessarily. But if we start to think about things we do know, even before we start to get into quadratic residues, I mean, we're going to try and argue about things modulo 8. So Q mod 8 must be, I think we talked about this before. What are the possibilities for a prime number modulo 8? First of all, well, you might think 2 or something, but notice that these numbers 8k plus 3, these are all odd. Okay, all of those numbers are odd. Anything congruent to 3 mod 8 is odd. So how is N? N is a product of a load of odd numbers, which is odd. squared it, which is still odd, added 2, which is still odd. Okay, so this is n is odd. So that means it can't be divisible by 2. So 2 is not an option. Well, if 2 is not an option, then the only options for prime numbers are 1, 3, 5, or 7. Okay, modulo 8. Everything else is either the prime 2, which we know is not allowed because n is odd, or can't be any of the other numbers 2, 4, or 6. Okay, those would be. Okay. So let's think of one of our, so Q is one of these 4. If we arrived at the statement that we could show that Q had to be, or that one of the Qs is definitely congruent to 3 mod 8, then we would be able to say, well, then it must be one of the PIs. Because we've assumed there's only a finite number of primes in congruent to 3 mod 8. So if somewhere along the way we reached a conclusion that one of these Qs, remember there might be multiple prime factors of n, but if one of these Qs was congruent to 3 mod 8, then we could say immediately, the Q must be one of these PIs, and maybe get a contradiction out of that. Then the PI would have to divide 2. PI divided n, it also divides this product thing here, so therefore it must divide 2, it must be equal to 2. We've already ruled out 2 as being a possible prime factor of capital N. So consider such a Q. We know Q divides n, i.e. Q divides this big square plus 2. And so this is where we can get the, this is where we start to get the quadratic residues. Because then, i.e. this big square plus 2 is going to be equal to AQ for some A. But then you're saying that what are we saying? You're saying that this thing squared is congruent to -2 modulo Q. Okay. Bring the -2 over the other side, so the square of this thing is AQ minus 2. So, i.e., -2 is a quadratic residue modulo Q. This is the Legendre symbol, remember? For indicating quadratic residues. So this, okay, so this is the answer to the question, why did we square all these up here? Because it allows us to connect with what we've established about quadratic residues. Okay? So if this bracket all squared is congruent to -2, so -2 is quadratic residue. But then we also know that the Legendre symbol is multiplicative. Okay? So it factorizes as -1 mod Q times 2 mod Q. Those Legendre symbols. And remember, we proved results about these. Okay. We have theorems, and as remember what we call them, we had theorems about -1 modulo prime and 2 modulo prime. They both told you what the values were in terms of congruence classes of the prime Q. This one, the first one related it to Q mod 4. The second one related it to Q mod 8. Well, that's really good because we're in the context of things mod 8 here. And if we know about things mod 4, we also know about the congruence class mod 8, okay, because the congruence classes of 4 match well with the congruence classes of 8. But what we do know is the product of these two is +1. So that means there's 2 possibilities. Right? Either they're both +1 or they're both minus 1. Okay. If they multiply together to give plus 1. So there are two cases. Either case 1, minus 1, q is equal to 2q is equal to minus 1. Case 2, both Legendre symbols are plus 1. So now we should, okay, everybody okay to there? Kind of arguing. And remember, still, that there are we have to consider that there might be multiple different q's, multiple different prime factors of this u number, capital N. But each of them will fall into one of these two cases. Either these two Legendre symbols will be minus 1, or they'll both be plus 1. So let's look back at what our results said. So these are theorems 8.5 and 8.6. So from these theorems, 8.5 and 8.6, in the first case, well, if minus 1 q is equal to minus 1, that means q is 3 mod 4. And, well, if 2q is equal to minus 1, then q is plus or minus 3 mod 8. Q is plus or minus 3, so that's the same as saying 3 or 5 mod 8. In the second case, if it's minus 1q is plus 1, that means q is congruent to 1 mod 4. And if 2q is plus 1, that means q is congruent to 1 or 7 mod 8. But in either case, both of the congruences must be true. Okay. Now, at the moment, we've just got the two congruences sitting there, statements on their own, but they must be simultaneously true. So combining the congruences gives the cases as, so how do those two congruences combine? Q has to be 3 modulo 4, and also Q has to be 3 or 5 modulo 8. How do you reconcile those two statements about Q? Can we reconcile them into a single statement about Q? Yeah, which is?
It's worth 3.
Well, just in case one.
Like it has to be 3 mod 8.
Okay, so why can't it be congruent to 5?
Because then it would be congruent to 1 mod 4.
Yeah. Yeah. So if Q was 5 mod 8, so it'd be 8 times something plus 5, but when you then tried and divided that number by 4, 4 goes in 4 goes in cleanly into the 8 times something. So then you're just dividing the 5 by 4, and you're going to get remainder 1. So it's going to be congruent to 1 mod 4. But it can't be congruent to 1 mod 4, it has to be congruent to 3 mod 4 within case 1. So within case 1, the only possibility is Q is congruent to 3 mod 8. And it will be 3 mod 4 as well, of course. Okay. But it can't be 5 mod 8. And then the other one, in case 2?
Same approach.
Same approach.
It has to be 1.
Has to be.
7 mod 8, 3 mod 4.
Yeah. Okay, so if it was 7 mod 8, it would be 3 mod 4. Okay. So that's Q equal to 5 mod 8 implies Q is 1 mod 4. Then here, similar justification is Q congruent to 7 mod 8 implies Q is congruent to 3 multiplied. Okay. So step back a bit. What have we said? We're doing proof by contradiction. We assume there's only a finite number of primes at the form 3 mod 8. We multiplied them all together. We squared them. We added 2. And now we're saying prime factors Q of this new number, capital N, must be 3 mod 8 or 1 mod 8. Three mod 8 or 1 mod 8. Now we kind of want them. We want to be able to say that case 1, Q congruent to 3 mod 8 must arise for some Q dividing N, because if we could reach that point, then we'd be able to say that that Q, because it's congruent to 3 mod 8, it must be one of these P's. So therefore, one of these P's must divide 2. Therefore, it's equal to 2, but there's your contradiction, okay? Because it can't, these are all congruent to 3 mod 8, so you can't have one of them divided 2. But how can we argue for that? Must one of the prime factors of Q be congruent to 3 mod 8? Question. Well, does everybody agree that that's what I want? Yeah. If we could show that case 1 must arise, then we could get the contradiction out. Well, okay, so it either arises, and then we can prove it. There is an infinite number of primes here, or it won't arise. But the problem is if it won't arise. So what if case 1 never arises, i.e., all the prime factors Q of N are satisfying this, that Q is congruent to 1 mod 8. We're in kind of like a mini proof by contradiction within our overall proof by contradiction. What if that happens? What might we be able to say from that? That might contradict something we've already got. So we're saying all of the prime factors of N are congruent to 1 mod 8. What does that tell you about N? How do the prime factors of a number relate to the number? Well, a number is the product of all of its prime factors, including their multiplicity. So some of the prime factors might go in multiple times. But whereas in a little mini proof by contradiction, here we're asking ourselves what would happen if all of the prime factors Q of N were congruent to 1 mod 8? What would happen?
Energy 1 mod 8.
N would be 1 mod 8. N, which is the product over these Q's, Q dividing N of Q's to some, well, maybe they have some power on them, alpha sub Q. But this would be congruent to 1 mod 8 because it would just be a big product of things congruent to 1 mod 8. And when you multiply things together, the congruence class the product is in is the product of the individual congruence classes. But is N congruent to 1 mod Does it look like something congruent to 1 mod 8? Can we say? Well, if all of its prime factors were 1 mod 8, then n would be 1 mod 8. But we've already got a construction of n up there. Can we tell from the construction of n what is n mod 8? Well, n is constructed like that. Anybody got a congruence class for n mod 8? Yes. Well, look at the way it's constructed, right? We multiply together all these p's. Now, the p's we know about. The p's are all 3 mod 8. Yeah. What happens when you multiply together a load of things that are 3 mod 8? Well, if you multiply 2 things that are 3 mod 8, you get 9, which is 1 mod 8. If you multiply it by a third thing that's 3 mod 8, multiplying 1 by 3, so you get back to 3 mod 8. If you multiply it again by something congruent to 3 mod 8, it goes to 9, so it goes to 1 mod 8. So products of things congruent to 3 mod 8 either give you 1 or 3, depending on how many of them are, whether there's an odd number or an even. So the value inside this bracket is going to be 1 or 3 mod 8. Then we're going to square it. If it's 1, it stays at 1 mod 8 when you square it. If it's 3, it goes to 9, which is 1 mod 8. So we can definitely say the bracket squared is congruent to 1 mod 8. And then we add 2 to it. Which is 3 mod 8. So recall that for all the i's, pi is congruent to 3 mod 8. So the product of all the p's is congruent to 1 or 3 mod 8, hence whether there's an even or odd number of them. So the product squared is has to be congruent to 1 mod 8. So the product squared plus 2, which is n, has to be congruent to 3 mod 8. So that contradicts this statement here. N is congruent to 1 mod 8. Now, we only reached that conclusion that n was congruent to 1 mod 8 if we suppose that case 1 never arose. That it was always true that every prime factor of n was congruent to 1 mod 8. So now we know that cannot happen, okay? Because it would contradict the way n was constructed. So case 1 must arise sometimes. In fact, you could say, an odd number of times. Remember, case 1 was prime factors congruent to 3 mod 8. So an odd number of times when counting multiplicities of factors. Multiplicities of the prime factors of n. Okay, but we're in this situation now that it must occur in this case, okay? Because if it didn't occur, we'd be simultaneously looking at a number n, which is supposed to be 1 mod 8 and 3 mod 8. And that's just nonsense, okay? It can't be 1 mod 8 and 3 mod 8. So it can't happen that case 1 never happens. So case 1 must happen at least once. So let Q divide n, and Q is congruent to 3 mod 8. This must happen at least once, so we can point to it and use it. Then, by the assumption we made at the top, Q is equal to one of the PIs for some I. Okay, because remember, overall we're in a proof by contradiction. So we made that contradictory assumption at the start. So now we're back to one of our PIs. So this PI must divide n minus the product of all the PIs. squared, which is 2. Okay. That's just by our basic result, proved in one of the first or second lectures, I think, that the divisibility of linear combinations. Right? Both these things are divisible by pi, then pi divides this linear combination. Well, if pi is a prime number and it's equal and it divides 2, that means pi must equal 2. So we got this conclusion. This conclusion isn't just one of the cases. This conclusion must happen. Okay. But now we're at a contradiction because we said at the very beginning, assume the P1 to S are all the primes here. Here, this sequence, everything in it is congruent to 3 mod 8. So now we're forced to say that the PI must be 2. Or another way of saying is that that's saying that n is even, but we've already noticed that n must be odd. So we're seeing the contradiction from multiple sides. Question?
Well,
Query? Yeah.
like PI. I mean, it doesn't change it, but PI is also equal 1.
Okay, well, I think I'm using the fact that it's already a prime.
Yeah.
Yeah, so it can't be 1. Yeah. So if it's a prime dividing 2, it must divide 2. I mean, you get this when you've reached the contradiction stage. There's often kind of multiple ways that the contradiction could be, you know. So I'm just kind of forgetting the assumption I've made that this here. I'm just considering this pi as a prime factor must divide 2. A prime dividing 2, it must equal 2. Then you kind of check back at the other things that you've already recorded or established or assumed. Yeah. But yeah, But you see, if we said that pi might be 1, but then we'd immediately discount that because we remember p is prime. So then we'd be forced to conclude that it has to be 2. And this is where we get a contradiction. But this is a contradiction. But this contradicts the very first assumption. This is not subject to any cases. This statement, pi equals 2, this must happen from the assumption. Okay, we thought we were in like a 2-case situation, but we realized that case 1 must happen. So we just took one of the case 1 primes, q, and argued from that. Okay, so this is a really nice. So it's a nice extended proof by contradiction. So we then get the so there are an infinite number of primes. Number of primes congruent to 3 mod 8. And it's a nice, you know, it's not just a 1-paragraph proof by contradiction like Euclid's original proof. You do have to do some work, and it brings in the theory of quadratic residues. But it illustrates really nicely the very idea of proof by contradiction. Yes, the very idea of proof by contradiction is you make some assertion, and then you demonstrate that just making that assertion leads to a contradiction. So that tells you that making that assertion is impossible. You can't assert that. So therefore, the opposite of it must be true. An infinite number of primes. So there, in part C, there's a further one for you to work on, which is, what's that? Things congruent to 6k plus 1. You're going to show there's an infinite number of primes there. You'll also notice that that involves squaring in the construction of n, so it's likely to rely on the quadratic residues. And I was thinking, when I was looking at the exercises I have here, it did occur to me, maybe the case 6n minus 1 can also be proved in a similar way to the case of 4n minus 1. When we proved 4n minus 1 in the tutorial on Friday, we didn't need the theory of quadratic residues. And I think 6n minus 1 can be proved in a similar spirit to 4n minus 1. And there are lots of other, these other special these other particular cases, pairs of parameters A and B, which you can prove this result. But you've already started to see like different methods being used, either relatively straightforward in the case of 4n minus 1 and maybe 6n minus 1, but then the need to talk about quadratic residues for the cases of 8, 3 mod 8 and 1 mod 6. So there's no kind of general, simple approach from what we know that would deal with every possible pair of parameters. So it does require some more theoretical investigation. Okay, we'll leave it there for this morning, and I shall see you all later.